Hey Team Pecan, and welcome to today's lecture, where today we're going to be talking about the rigid rotor model and rotational spectroscopy. So I'd actually like to begin today's discussion with a little bit of a recap from some of the previous lectures that we've done on vibrational spectroscopy, this time presented in somewhat of a flowchart style so that we can really pay attention to the process that we used in trying to understand an IR spectrum. Where we started was that if we want to understand vibrational transitions, we have to have a model for the potential energy that describes a sort of bond vibration. In our lecture series, we came up with two such models. One that I'll be using purple to denote, the harmonic oscillator model, which is really good at trying to understand what bond vibrations look like close to the equilibrium geometry, and a second model, the Morse potential, which I'm going to depict in green, that describes not only that near equilibrium region, but also describes how bonds dissociate at large internuclear distances and how they compress a little bit more quantitatively at short internuclear distances. And so with that model, regardless of if you're using this harmonic oscillator approach or if you're describing things using a Morse potential, we have a model for how the potential energy should change as a function of our internuclear distance. And so once we have this model for the potential in mind, now we can go ahead and undergo the process of solving the time-independent Schrodinger equation to describe this motion, not just in terms of our classical model, but in terms of a quantum mechanical model. We underwent that process of solving the time-independent Schrodinger equation, and we found that there's two different but somewhat related expressions for our harmonic oscillator and for our Morse potential. Oftentimes, you're going to see chemists depict these energy levels superimposed on top of the potential energy surface for that classical model. And so you may see your energy level diagram drawn with these lines that should be evenly spaced apart in the case of the harmonic oscillator model. And for our Morse potential, should start off really close to our harmonic oscillator model, but eventually start to get line spacings that end up closer and closer together in energy up until the point where the molecule dissociates entirely. Once we have this model for our quantum transitions and these discrete energy levels, the next step that we underwent in our lecture series was to use the transition dipole moment, that's that mu-t expression, to develop the appropriate selection rules for IR spectroscopy. Those selection rules are going to tell us which peaks are expected to show up in the IR spectrum corresponding to allowed transitions versus the peaks that are not expected to appear in the IR spectrum because they're forbidden. Using our harmonic oscillator model, we developed selection rules that the change in the vibrational quantum number nu has to be either go up by 1 or go down by 1, and that as the vibration occurred, that the dipole moment of the molecule had to undergo a change. The Morse potential had similar rules to the harmonic oscillator, except that it said, no, actually, some of these overtone transitions, where delta V is greater than plus or minus 1, should also be allowed. And then last but not least, we can use all of this information to try and understand, either to predict an IR spectrum if we want to use computational chemistry, or to try and interpret a pre-existing experimental IR spectrum. And what we know is that using our spectrum, these transitions are going to, if I see a peak in the IR, I know that the wave number corresponding to that peak tells me the energy of a photon. And that energy of the photon is going to be exactly the same as whatever the gap is between my V equals 0 and my V equals 1 level for that fundamental transition. And so this is the connection then between my IR spectrum and all this quantum mechanical work that I did. My energy level diagram tells me what delta E should be. So does my IR spectrum. And so if I know some information about a problem, I can often use the IR spectrum to help me understand bond force constants, for example, or isotope effects as the reduced mass mu changes between systems. And similarly, if you start from the other end of the problem, if we can use quantum chemistry and computational chemistry to come up with reasonable approximations for K and for mu, then we can go ahead and predict an IR spectrum for molecules that we haven't been able to observe before. Today's lecture goal is going to be to go through this same process, except instead of considering vibrational motion, today we're going to consider rotational motion. And so let me present today's lecture goals again in the form of questions. The microwave spectrum for a typical molecule like carbon monoxide ends up having many peaks in this microwave region. And what we want to understand is, wow, carbon monoxide seems like such a simple molecule. Why would it lead to so many peaks? And the flip side of that question is, why is the spectrum useful? In other words, is there chemical information that can be obtained from a microwave spectrum like the one shown for carbon monoxide? The other question that we want to try and address today is sort of a mystery that you may or may have not have noticed in looking at some vibrational spectrum up to this point. Like we walked through in the last lecture, we can do a computational chemistry calculation. In this case, this figure corresponds to a B3-lip computation with a triple zeta basis set. And like you could predict from the fact that this is just a simple diatomic, carbon monoxide should have a single vibrational peak. ChemCompute told me that this should appear around 2140 wave numbers once I do the appropriate scaling of my DFT computation. And so my IR spectrum should look really simple, one peak. However, when I look at the NIST database for experiments on carbon monoxide, I actually see two peaks in the IR spectrum. And if you are able to do a highly resolved IR spectroscopy experiment of carbon monoxide, really focusing on that near 2000 wave number region, a high resolution IR spectrum will in fact tell you that those two peaks correspond to many, many, many different peaks in the IR spectrum. And this should be surprising to us. And a question that we might ask is, what's happening in this case? The answer is going to be connected to rotational spectroscopy, which is why this sort of multiple peak situation in our IR spectrum is also going to be a subject for today's lecture. All right, and with that, let's go ahead and get started. Before we can talk about quantum mechanics for rotational motion, we have to do a little bit of a review of the quantum mechanical model for the particle in a sphere, which was a lecture topic all the way back at the beginning of the semester. Recall from that discussion that our particle in a sphere model said that the potential is zero, so the particle can freely move so long as it's on the surface of this sphere, but don't you dare change r, the distance between the origin and where the particle is at. Otherwise, the potential is going to go up to infinity, and the particle is not going to be allowed to exist in that region. We did the arduous process of solving the time-independent Schrodinger equation for this potential, and we realized that the wave functions are none other than the spherical harmonics. And the energy expression, fortunately, is much more mathematically simple. It's that the energy levels for a particle in a sphere are given by a quantum number L times L plus 1 times Planck's constant, h bar squared, divided by 2 times the mass of the particle times r squared, where r, capital R, is the distance, that fixed distance between the origin and the particle. In our particle in a sphere treatment, there was a second quantum number, m sub L, and because the energy levels only depend on L, each energy level ends up having a degeneracy of 2L plus 1. So if L equals 0, m sub L can only equal 0. If L equals 1, we have 3 allowed values of m sub L, -1, 0, and 1, and it goes on up from there. And so hopefully you can see what I mean by that degeneracy of 2L plus 1. Because m sub L can be between -L and positive L, as we go up in L values, we get more and more allowed levels. With that review, now we can talk about the rigid rotor model. So a rigid rotor is very similar to a particle in a sphere. The only difference is that instead of having one particle attached to an origin at a fixed bond distance, now I have two masses that are free to rotate about this axis, but are not allowed to change their bond length. And so our rigid rotor is a system that has still that fixed value of capital R denoting the distance, but just two masses instead of one. So the quantum mechanical solutions to this system end up being nearly identical to that of a particle on a sphere. The only difference is that our mass m from the particle on the sphere gets replaced by the reduced mass mu, where just like when we were talking about vibrational motion, mu is equal to the product of my two masses divided by the sum of my two masses. And we're going to rename our rotational quantum numbers because L and m sub L are already used up for the hydrogen atom. And so we're going to call our rotational quantum numbers J and m sub J. And again, that's nothing that's conceptually changed from our previous model. It's just that we want to avoid confusion with electronic spectroscopy. So our rigid rotor energies then become h bar squared divided by 2 mu times r squared times j plus 1. And again, I just want to point out that this really is identical to those particle on the sphere energies, aside from the changes that I just noted. Often, spectroscopists like to group together these constants that show up in front into a term that's called B. And so it's shown here, but just remember that B is equal to h bar squared divided by 2 mu times r squared, where r in this case now represents the equilibrium bond distance of this diatomic molecule. So sometimes you'll see in textbooks people throw an r sub e down here in order to remind us that it's the equilibrium bond distance that we're talking about. Just like before, each energy level has a degeneracy of 2J plus 1. As with vibrational spectroscopy, it's really helpful to calculate what's the energy difference between successive levels. And in this case, if I take my rigid rotor energies and I subtract the energy of the J plus 1th level from the energy of the Jth level, I wind up with a fairly simple expression, especially if I term it in terms of B, which is that delta E is equal to 2 times B times the quantity J plus 1. And this expression is so interesting, in fact, that what I'm going to have us do is tackle a couple of critical thinking questions related to our energy levels and to our delta E expression. Unfortunately, I can't put the energy level and the delta E on the slide at the same time. Hopefully you've copied it down. But what I want you to do at this point in the video is try and tackle in turn each of these 4 critical thinking questions related to this rigid rotor model. Pause the video, and when you come back, we'll go through them together as a group. All right, so our first question is, how many solutions to the rigid rotor have an energy of 10 times B? In other words, what's the degeneracy of the level that has energy 10B? Well, the first thing we need to do is notice that if the energy is 10B, that means that our quantum number, well, it has to be something interesting. In fact, our quantum number is going to have to be J equals 4. Oops. My apologies, folks. This should have said 20B. You were looking at this and were not sure what our value of J was. because I made a typo. Sorry, folks. If we talk about 20B, though, that would mean that J has to equal 4. So that would give us J 4 times 5. That'll give us a value of 20B. And in this case, if J equals 4, so the degeneracy is 2J plus 1 equals 9. There are 9 solutions to the rigid rotor that have this energy associated with it, which is a lot of levels. Okay, question 2. Hopefully no typos from here on out. According to our rigid rotor model, should the spacing between energy levels increase or decrease as J increases? This one's pretty simple. We have our expression for delta E, and we see that it depends linearly on J. So if J increases, delta E is going to increase. And that means that our spacings between energy levels are definitely going to increase as J increases. Question 3, which of these two systems is going to have a larger spacing between energy levels? Should it be HCl or DCl? Well, in this case, we're going to have to think about what the difference is between these two molecules. And the difference is nothing to do with their bond distance, really. Deuterium adds an extra neutron onto this HCl molecule, but it doesn't change any of the chemistry. What does change is the reduced mass mu. And so in this case, we have to figure out which of these two quantities has the bigger value of mu, and therefore, which of them would be expected to have the greater delta E, which is going to be inversely proportional to mu. And so in order to calculate these quantities, it's helpful for us to pull up maybe an Excel spreadsheet in order to do this, or at least I like doing this in Excel so that I can have all of my quantities written down correctly. And so using our Excel spreadsheet, we can pull up a few of our fundamental constants to begin with. Switch screens. And the quantities, the masses that we're going to want to include on this spreadsheet are going to be the mass of our hydrogen, the mass of our deuterium, and the mass of our chlorine. And I'm going to write these all down in terms of grams per mole to start off with. But pretty soon, we're going to change this into units of kilograms so that we can compute mu appropriately. So for HCl, our first mass is equal to the hydrogen mass divided by Avogadro's number so that we're in units of grams per atom. And then similarly, normally you want to represent these masses in terms of kilograms for us to be able to use later. So our mass of our hydrogen is going to be 1.67 times 10 to the negative 27th kilograms. Our chlorine mass, similarly, is going to be the same process, but for our mass of 35 grams per mole, divide that by Avogadro's number, divide by 1,000, and we get M2 is equal to 5.81 times 10 to the negative 26 kilograms. That means that mu, as always, is going to be the product of these two masses divided by the sum of the two masses. And that will give us, once I type this into Excel correctly, that'll give us our reduced mass for HCl. For DCl, it's going to be the same process, just that M1 is going to change in order to be our deuterium mass. And so for our deuterium mass, divide by Avogadro's number, divide by 1,000, we see that M1 for deuterium, as we might expect, is a little bit bigger. M2 should be the exact same. And our reduced mass is going to be calculated using the same formula, but we'll see that our reduced mass for DCl is a little bit bigger than that for HCl. So now that we know that as a molecule has, a more even mass, mu, the reduced mass, gets a little bit bigger, now we can confidently say that for HCl, mu is smaller. And therefore, a smaller mu is going to lead to a bigger delta E. So bigger delta E means that HCl has bigger spacings compared to DCl. So that's our answer to question 3. Delta E is bigger for HCl. And then last but not least, we have a slightly more quantitative question. Carbon monoxide has a bond length that we know experimentally to be about 1.13 angstrom. And so what energy in joules do we need to undergo a rotational transition from the J = 3 level to the J = 4 level? Well, in this case, we need to use our formula, delta E is equal to h bar squared times J plus 1 divided by 2 mu r squared. So I've taken the liberty with calculating what mu should be for our carbon monoxide molecule using the isotopes of 12 for carbon and 16 for oxygen. You can check my math on this, but the mu value for carbon monoxide ends up being 1.14 times 10 to the negative 26 kilograms. Similarly, we have our bond distance, which is 1.13 times 10 to the negative 10 meters. Again, I'm doing everything in SI units so that when we get our energy, it'll be in units of joules. And J is equal to 3 because we're doing the transition from J to J plus 1 in order to use our formula correctly. Plugging in all this information, and again, I'm doing this in an Excel spreadsheet because it really saves you time compared to typing this into your calculator. We have that delta E is equal to h bar squared times J plus 1 divided by mu times r squared. And if you plug this into your Excel spreadsheet, you're going to get that delta E is equal to 3.06 times 10 to the negative 22nd joules. And as a sanity check, we know we're talking about a fairly excited rotational transition, so it's going to be a little bit bigger energy than that 10 to the negative 23 that I gave us as a rule of thumb for rotational transitions. But we're still in that ballpark. And if you get an answer that's a way off in terms of orders of magnitude, you know you probably made a mistake in your unit conversions. All right, so let's transition now to talking about our selection rules for microwave spectroscopy. As we learned earlier in previous lectures, rotational transitions occur with photon energies somewhere around 10 to the negative 23 joules. That corresponds to the microwave region of the electromagnetic spectrum, and hence rotational motion is often frequently studied using microwave spectroscopy, which is going to give us wave numbers from kind of 1 to 100 inverse centimeters. Just like with vibrational spectroscopy, to solve for the selection rules of microwave spectroscopy, we have to solve for the transition dipole moment. And that transition dipole moment is given just like before with the wave function for the final state, complex conjugate, times the quantum mechanical operator for the dipole moment. Again, I know that folks are using, or in this case, we've sort of run out of Greek letters, so we have to pay attention to context to know if mu is talking about the reduced mass or the dipole moment. In this case, this is talking about the dipole moment operator. And we're going to multiply that in the integrand times the wave function for the initial state. Integrate over all space, and that is our transition dipole moment. Because our wave functions for the rotational motions are the spherical harmonics, we ultimately end up with an integral expression that looks pretty simple, although the integral is nothing but simple. You get that the transition dipole moment is either equal to mu squared, again, dipole moment, not reduced mass, times j plus 1 divided by 2j plus 1, assuming that the initial and final states are separated by only a change in quantum number of plus or minus 1, and either 0 or plus or minus 1 for m sub j. Otherwise, the transition dipole moment is equal to 0. And so consequently, the selection rules for microwave spectroscopy are that the molecule must possess a permanent dipole moment. You'll notice that if mu, our dipole moment, is 0, the transition dipole moment is 0 regardless. So that's why we need a permanent dipole moment for this molecule. And then similarly, our transition states have to either go up or go down by this quantum number j, otherwise the transition dipole moment is 0, and that would correspond to a forbidden transition. Now that we know our selection rules, we're finally ready to tackle what a microwave spectrum looks like and how we can interpret it. One thing to notice, and is a point of contrast between vibrational and rotational spectroscopy, is we have to remember that the vibrational modes, for reasons that we'll explain a couple lectures from now when we talk about statistical thermodynamics and the Boltzmann distribution, nearly all molecules at room temperature are in their vibrational ground state. And so the only transition that we see in the IR spectrum is the nu equals 0 to nu equals 1 transition. So each vibrational mode in the IR spectrum corresponds to more or less one vibrational peak. By contrast, molecules at room temperature are often found in low-level vibrationally excited states. And so I'm not surprised when I see a transition from the j equals 9 to the j equals 10 level, because it's low enough that that state can, like a molecule can exist in a rotationally excited state. Again, we're going to have to wait until a couple lectures from now to really understand the basis for why it is that vibrationally we're always in the ground state at room temperature, but rotationally it's easy to be in some of these low-level excited states. Because the transition energies in turn depend on our quantum number, J initial, this in turn gives rise to many peaks in the microwave spectrum for a given rotational mode. And so a question that I want us to solve as a group is, again, here I'm writing down one more time my expression for delta J, that change in energy for going between rotational levels. But let's try and interpret this spectrum for carbon monoxide shown above with what transitions correspond to each of the above peaks. So go ahead and pause the lecture video and try and fill out this table for J initial, J final, and the corresponding delta E. I'll do the first row for us so that you can see how I'm going to express all these energies in terms of B, not worrying yet about solving for mu and R. So if J initial equals 0, we have to go up by 1, so J final is going to equal 1, and our delta E for this transition is going to be 2B, since J initial, our J value, is equal to 0. Go ahead and pause the video, see if you can fill out the remainder of this chart, and then based on those energies, see if you can interpret which transitions correspond to which peaks in the spectrum. Okay, so now that you've come back and had a little bit of time with this, hopefully you see that filling out J final is super easy. We're just going to add 1 to our J initial values, and then taking this value of J initial, that's going to help us solve for delta E in each case. So the 1 to 2 transition is going to correspond to 4B, 2 to 3, 6B, 8B for the next transition, And finally, 10b would be the delta E corresponding to the j equals 4 to j equals 5 transition. And so since delta E corresponds to where we see the peak in a spectrum, this first peak corresponds to an energy of 2b, 4b, 6b, 8b, etc. And that helps us interpret the peaks that at lower energies, lower transition energies, that would be our j equals 0 to 1 transition. 4b would correspond to the 1 to 2 transition. 6b, our 2 to 3 transition. And we can keep going on up from there. So these different rotational modes tell us what rotational states are present at room temperature to start off with. And then those transitions correspond to us gaining just a little bit of rotational energy in order to give rise to these peaks in the microwave region. Something that's really interesting to point out is that delta E between all of these different levels goes up by a factor of 2b. And so for this reason, the spacings between peaks in the rotational spectrum are constant, with that energy spacing always equal to 2b. So if you noticed in our microwave spectrum that these peaks were spaced out really nicely, that's not a coincidence. It's something that's coming from our quantum mechanical energies. And so if you wanted to figure out what B was based on a microwave spectrum, one way to do it would be by looking at an individual peak. But a second way to do it would be by looking at our peak spacing and setting that equal to 2b. Okay, so now we know how to interpret a microwave spectrum, but why is it useful? It turns out there's a lot of chemical insight to be gained from a microwave spectroscopy experiment. And while there are many different areas of application, one area that I think is really neat is in the area of astrochemistry. So in general, microwave spectroscopy is a valuable technique primarily for obtaining molecular structural information. For instance, bond lengths, bond angles, or different properties of a molecule's geometry. And in interstellar space, it turns out, and I think this is a really good article that I've also thrown up on Moodle that highlights this issue, microwave spectroscopy gives rise to much cleaner spectrum in interstellar space compared to higher energy spectroscopy. And so microwave spectroscopy is also used in astrochemistry because it's one of the only spectroscopy techniques that can be used to understand what molecules are present in the interstellar medium. And so in an article like this for astrochemistry, as well as other articles, those are the primary two uses for microwave spectroscopy. First, we can understand without having to disturb the molecule's environment, or even by being able to study molecules that are very, very far away from us, we can use microwave spectroscopy as a chemical fingerprint to understand what molecules are present in a particular environment. And not only can we identify the presence of those molecules, but we can use the spacing between peaks in the microwave spectrum in order to understand what geometric properties that molecule has. And I'll show you an example of that in just a moment. But I want to show you as kind of a case study that, for example, in the article shown at right, they used microwave spectroscopy to first prove that a sulfur monoxide ion exists in space, and two, they were able to determine its bond length. And so let's do an example of that exact same process, except we'll use carbon monoxide as our example since that's what we've been consistently using throughout today's lecture. So our rotational spectrum for carbon monoxide is shown at right, and I've done a little bit of work to guesstimate where some of these peaks show up. And so I'll give you the fact that our peak corresponding to the J equals 3 transition, so J equals 3 to J equals 4, appears at about 15 inverse wave numbers. And our peak corresponding to the J equals 4 to the J equals 5 transition shows up at about 19 wave numbers. So once again, go ahead and pause the video and see if you can use this information to calculate the bond length of carbon monoxide. All right, now that you've had a chance to do this, let's go through the problem together. So we know that the spacings between peaks should be equal to 2b. And using that information, we can determine that 2b, and I'm going to put a tilde above it since we're in units of wave numbers to remind ourselves that this is not b in units of joules, but our 2b is equal to about 4 inverse centimeters. When we convert this to units of energy, we obtain a value for B that is approximately 3.98 times 10 to the negative 23rd joules. I'll show you the Excel spreadsheet I'm using in just a moment to calculate this, but again, really helpful to use Excel in these situations. We've already calculated mu for a carbon monoxide molecule, and so let's go ahead and write down that value one more time, again in units of kilograms so that we avoid unit conversion errors. And so given the fact that we know B and we know mu, solving for our rotational constant, our equilibrium bond length is not too bad. The only thing that we need to remember from above is what the value of B means. And B corresponds to h bar squared divided by 2 mu r squared. So B is equal to h bar squared divided by 2 mu equilibrium bond distance squared, which means that R equals the square root of h bar squared divided by 2 mu times B. Plugging in those values for our equilibrium bond distance, we get that R is equal to 1.1 angstroms. And compared to the value of 1.13 that you get from Wikipedia, that's really good. And in fact, after doing this calculation, I looked up what the better value for 2b is equal to. If we, instead of just guesstimating from the spectrum, we were able to actually look up the results. And it turns out that B is equal to 1.92 inverse centimeters. If you plug that in, that's going to give you your bond distance in units of meters that corresponds exactly to where that experimental bond length is. And in fact, for a long time, especially before the advent of IR or for X-ray diffraction experiments, and even now, especially if you want an in situ way to determine an experimental bond length, rotational spectroscopy is really the way to go. So a lot of the information that you look up on Wikipedia for, what's the bond length of these simple molecules, that information was originally obtained using microwave spectroscopy. All right, so our last topic for today is going to be combination spectroscopy, rotational vibrational spectroscopy. This is that second mystery that we outlined at the beginning of today's lecture. So as I mentioned originally, the experimental IR spectrum is much more complicated for carbon monoxide than we might have expected. Instead of observing one peak for that one vibrational transition, at low resolution we observe 2 peaks with the chem-compute prediction kind of showing up right in the middle of the 2 peaks. And in our higher resolution spectrum, we see the existence of many, many peaks. And now that you've seen a microwave spectrum, it kind of looks like there's 2 mirror image microwave spectrum put near this vibrational peak. And in fact, that's more or less exactly what's going on. The existence of extra peaks in the IR spectrum can be explained by considering how a molecule's vibrational excitations, so as I bend or stretch this molecule, often can induce a corresponding rotational transition. So this is a pretty complicated looking diagram to explain these combination rotational vibrational transitions. So let's unpack all that's going on in this diagram in turn. The first thing that I want you to notice, not yet paying attention to the arrows, just paying attention to the energy levels, is that just like how the electronic transitions had to be described by multiple quantum numbers, when we want to understand both rotations and the vibrations associated with a molecule, we have to combine together its vibrational and rotational quantum numbers. And so a molecule that's present in the total ground state, the vibrational ground state and the rotational ground state, is going to have quantum numbers of nu equal to 0, as well as j equal to 0. So this is one energy level that the molecule can be present in. And at room temperature, we expect all the molecules to be in this nu equals 0 vibrational ground state, but aren't too surprised when the molecule exists in any one of these different rotational states that are a little bit excited. So you'll notice that the arrows drawn on this diagram representing my various transitions all start in the nu equals 0 state, but can start from any one of these different rotational states. In terms of the excited states, now we have vibrational excited states that are all going to be at much higher energies. In fact, I would say that this delta E gap is not really to scale. Should be much bigger than that, really about 1,000 times bigger than this is. But again, we have rotational states that correspond to what the molecule can do in these vibrationally excited states. And to a pretty good approximation, if we want to consider the energy of something in the rotational ground state but the vibrational excited state, we just need to add up the energies of the vibrational plus the rotational. So the tops of our arrows corresponding to the final states of these transitions, once again, are all going to be in this nu equals 1 state and at various energy levels. However, not all transitions are possible, which is why there's only a few arrows present on this diagram. In fact, rotovibrational transitions have the selection rules that delta nu has to change by plus or minus 1, and delta J also has to change by plus or minus 1. So only the purple and the red transitions shown on this diagram are typically observed. This so-called Q branch, where delta J doesn't change by anything, this would be what ChemCompute would predict because it's just giving us the vibrational frequencies, but it's a forbidden transition, so we don't see it on the IR spectrum. And as with many things in life, because there are so many rotational transitions that are present, scientists have grouped these transitions into categories. The set of peaks that correspond to J increasing by 1 as the vibration occurs are termed the R branch, and the derivation of that name comes from the fact that they were called rotationally rich peaks, R. If delta J is equal to 1, so we're exciting vibrationally but losing a little bit of rotational energy in the process, those are termed the P branch for rotationally poor excitations. And since our R branch is gaining rotational energy as it gains vibrational energy, we expect those peaks in the R branch to show up at higher energy values. Peaks coming from the P branch show up at slightly lower energies. And something to be cautious of, a mistake that I made as an undergraduate, was always assuming that on a given spectrum, the P branch was going to show up to the left and the R branch was going to show up to the right. However, spectroscopists are not consistent about whether or not they represent their x-axis in order of increasing energies or in order of decreasing energies. And so what you want to keep in mind when you're trying to look at a spectrum and figure out what's the R branch, what's the P branch, is the R branch should be closer to the higher energy end of the spectrum, and the P branch should be closer to the lower energy end of the spectrum. And so in fact, if we look at our spectrum up here, we can label now these peaks in the carbon monoxide spectrum as the higher energy peaks, R branch, and the lower energy peaks, P branch. Again, this particular spectrum is reported in inverse wave numbers for the red spectrum, and so we gotta label our R branch and our P branch appropriately. And conceptually, what I want us to realize is that ChemCompute really did do a good job of predicting where the vibrational transition should occur. It just didn't do any extra work to tell us that that is a forbidden transition, and what you would see in a highly resolved spectrum is a set of peaks corresponding to that vibrational transition plus some added rotational energy, or that transition minus a little bit of rotational energy. And so instead of seeing one peak for a molecule like carbon monoxide, you see two sets of peaks. All right, and that's all that I've got for us today. Some takeaways from today's lecture are as follows. First off, I want us to recognize that microwave spectroscopy is an invaluable and still currently used tool for either A, calculating structural properties of a molecule, especially in situ where you don't want to disturb its environment, and B, microwave spectroscopy is still used for chemical identification. We gave an example of how that gets used in astrochemistry to explore the interstellar medium, but it also gets used in many other fields today. A second takeaway is that in order to understand rotational transitions, the rigid rotor is an approximate but very useful model of how molecules rotate without necessarily changing their bond lengths. That's the approximation bit, since we know that real molecules vibrate a little bit. Based on that rigid rotor model, the wave functions are the spherical harmonics, and the energies are given by a fairly simple expression that takes into account the reduced mass and equilibrium bond length of the molecule, along with our quantum number for rotation, J. We also talked today about the selection rules for microwave spectroscopy. To be microwave active, a molecule has to have delta J either goes up by 1 or goes down by 1, and the molecule must possess a permanent dipole moment. So while we can generate a microwave spectrum for carbon monoxide, we wouldn't, for instance, be able to generate a microwave spectrum for H2. A fourth takeaway is that because rotational transition energies are small, low-lying rotational excited states are populated at room temperature. So when we use light to excite these motions, we get more peaks in the microwave spectrum compared to what we observed for vibrational spectroscopy. And then last but not least, rotational transitions can accompany vibrational ones, and hence highly resolved IR spectrum show multiple peaks per fundamental vibrational transition. And what I want us to gain from this is, again, rotational vibrational spectroscopy is a rich field in its own right. There's a lot of chemical insight. But for our purposes, since we're only spending one day on rotational spectroscopy, I want us to observe from vibrational spectrum that we might see in real life, that if you see a group of peaks closely spaced together in the IR, or if you see a doublet like we did for our low resolution spectrum of carbon monoxide, you may very well be observing rotational vibrational transitions rather than additional types of vibrations within the molecule. So with that, that's all that I've got for us today, and I look forward to seeing you all come lecture, or come class time. See you, folks.